the quantum revolution. Now this is 1900, and this is Max Planck. You probably remember him from honors chem. Now what he does is he's studying these things called black body radiation, and I'm not going to go into the history of the black body radiation. It is an interesting experiment, but we want to kind of get to the meat of the material here. So what he did is he discovered that energy is quantized. Now this is kind of a strange idea. Now classical physics, this would be what is known as Newtonian physics, says that we can have, again this would be classical, okay, that energy can take on any form that we want, or at least it's continuous and smooth, and we see it transfer from one to the other. So as energy increases, it's a smooth gradual change from one to the other. Think about turning your lights on it with a dimmer switch. You turn them on and you can slowly turn the light up, and it gets brighter and brighter and brighter. There's more energy coming out of it. What Planck said is that's not really what's going on. We think that's what's happening, but really the modern view of energy, what we think of, and again he didn't say modern because he didn't know about this being modern, but he said that really what happens is that energy is not really this smooth continuous motion, but actually this stair step, this idea that energy can't be one or the other. It's actually this either on this step or this step. There's no in between. You're either here or here or here or here. Energy cannot take any form that we want. Now this was really strange. Now to us it doesn't seem all that remarkable, but back then it was pretty monumental to these scientists to have this idea. They really were not liking this idea too much because we don't think of energies like that, right? I mean, think about getting in your car. You hit the gas pedal, and as you increase the energy by pushing the gas pedal down, you slowly get faster and faster and faster and faster and faster, right? Well, what Planck is saying is that that's not the case. He's saying you stay at this speed. So you hit the gas pedal, you stay at this speed, and then all of a sudden you do this huge jump from here to here, right? There's no in between. That's what he's saying. There's no energy in between, so it's not the smooth continuum, but more of a jerky jump motion. So you hold the gas pedal down, you don't move until all of a sudden you get to 20 miles an hour, boom, you're there. So you're at 10, no 15, no 12, all of a sudden, boom, you jump to 20. And you're at 20, and then you hit the gas pedal more and go further down, all of a sudden, boom, you're at now 30. Without 21, 22, 23, that doesn't seem right. I mean, if you think about that, that just doesn't seem like what's happening, but Planck said he thinks that's what's going on. Now, even though Planck came up with this idea, he wasn't too happy with it either. He kind of thought that this idea of quantized energy is kind of okay, because what happened was he used this quantized energy with his calculations, and it worked out great. I mean, if it worked out, everything worked out fine. But the problem was he didn't think it was real. He thought it was just a mathematical calculation or a mathematical trick that kind of led to an explanation of what's going on. Well, this is his equation. I'll get back to his story in just a second. This is the equation for his quantized energy. Okay, now this is an overly simplified version, but this here is the frequency from our previous equation. Remember, C is equal to wavelength and frequency. Okay, so what he does is he says that energy is connected to whatever the frequency is of the light we're talking about, or of the electromagnetic spectrum, because the electromagnetic spectrum has a bunch of different frequencies and wavelengths in it. So you have Planck's constant. Notice how small it is, to the negative 34 power. That's why scientists didn't discover this in the beginning, because the stair step that we're talking about, if I go back to this previous slide, the step here that we're talking about is really, really, really small. So if I magnify this up to a huge, if I go down to that scale, I'm going to see this stair step in here. And that's what Planck was saying. He said it's just really, really small. But even so, he didn't think it was fundamentally true. He actually was trying to disprove himself and actually trying to show that he was wrong. And it's kind of weird, but that's what he was doing. He's trying to fix it. He's trying to correct for this mathematical calculation. Anyway, H is indicative of quantum mechanics, by the way. Anytime you see H or Planck's constant, you are dealing with quantum mechanical level work. So what's going on here is that we find that HV is the energy that's going to exist at the smallest level. So that's the smallest quantity of energy that's being released or absorbed. So what we find is that actually the light that's hitting you right now from the computer screen is actually hitting you in little tiny bursts that he called quanta. Okay, so you can do some calculations with this. Again, I'm not going to do these calculations. They're pretty straightforward. E equals H. We'll look at some in class and you can start asking some questions about it, but really it's just a matter of plugging into some relatively simple equations, in the sense that they're simple because there's only two variables. C and E are always going to be constant. Okay, I'm sorry, C and H are constant. Okay, C is the speed of light. By the way, just so you know, speed of light is going to be 3.00 times 10 to the 8th. 10 to the 8th meters per second. Okay, so that's quantized energy. Now, as I said, all these scientists are scrambling to try to make sense out of this, and they're like, wait a minute, it's quantized energy, it's not real. So something's got to give. And this is where young minds come in. This is where the fresh, young brain comes in, because all these old guys didn't want to go with this. They thought it was kind of crazy. So it took somebody to really kind of take this idea and run with it. And the person I'm talking about is Einstein. Einstein, and this is getting into stuff you don't need for the AP test, by the way. So this is just some background information just to kind of give you some connections here. So anyway, so what Einstein does is he says that light actually is quantized, and he does what's called the photoelectric effect. Now, we'll talk a little bit more about this in class, but what the photoelectric effect is, if you have a piece of metal and you shine a light on that metal, okay, you shine some kind of light on it. So if I have like a flashlight or something here, and I shine some kind of light on this, what happens is electrons will be ejected from the metal. Okay, but this didn't happen with all light. If I did this with red light, the electron didn't come off. But as soon as I used a different color light, like green or blue, the electron came off. So using classical physics couldn't explain this phenomenon. Why was it that one color light wasn't working but another color light was? Well, what happened is that Einstein said that light is using this idea of quantized energy, because each color of light is connected to a frequency. He said that the red light lacked the energy needed because it didn't have the right frequency to knock the electron off. But if you use green light, the frequency goes up, so the energy goes up, and therefore the electron is ejected off the metal. So he uses this idea that everybody else is trying to fix and get rid of. Einstein kind of embraces it and then uses it as an explanation of what's called the photoelectric effect. And then he ends up winning the Nobel Prize for this. Alright, consequence of this though. Because of the fact that this electron is moving and I'm hitting it with energy, right? This is energy. And there's an electron which is a particle. Energy is not supposed to interact with matter like this, right? You think about shining a light on a piece of paper or something. The paper doesn't move. The paper is an object. No matter how bright the light is, right? You're never going to get that paper to move around. So what's going on here? Well, Einstein says that light has to be made up of particles. So instead of waves coming out of here, he said that what has to be coming out of the light are particles, because those particles have to collide with the electrons. But that's a problem, because our buddy Maxwell Clerk said that light is a wave. And there's experiments to show that they are. So that really brought, it solved one problem, but replaced it with another. So what is light? Is it a particle or is it a wave? And it's really boggled scientists for a while. Now, the last thing I'm going to talk about is matter waves. So de Broglie is looking at the work Einstein did, and he says, okay, so you're saying that light can behave as a wave, but it also acts as a particle. He did the opposite. In this equation, you're never going to have to use it, but I just have it up here just to kind of show you, because it's kind of interesting. What he says, we're going to need this idea later on anyway. So what he says is that, hey, you know what? I think that maybe an electron, which we said is a particle, maybe the electron is a wave. Right? Maybe matter itself behaves as a wave. So these are what are referred to as matter waves. And this is a really bizarre concept, but you can't just get rid of it and say it's wrong. If you have a mass and it has a velocity, now this is back to velocity, this is in frequency, and it's moving, this is momentum. It's a particle moving, Planck's constant, so we're down to quantum mechanics again, will have a wavelength. This is anything, you and me and balls and rocks and baseball, whatever. Anything that's moving with a velocity and has mass has a wavelength. Now, if you calculate your wavelength, put your mass in here and figure out how fast you're running, you can figure out what wavelength you're propagating in space. But the problem is it's going to be really, 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 really small. This wavelength will get bigger as the mass gets smaller, right? So as a smaller mass, a higher wavelength. So for an electron, which has a really, really small mass, the wavelength is going to come up to about -10 centimeters. Now that's something we can kind of measure, right? This is now getting into measurable quantities. Now that's a crazy idea that light can behave as a wave, and now particles can act as a wave, like electrons. But just because we say it doesn't mean it's true. So you need an experiment. Einstein had the photoelectric effect. What de Broglie is going to have to prove that he's right, and again, he didn't do this, but somebody else came up with it later, was that they used what's called X-ray diffraction. Okay, you don't have to worry too much about this, but what happened was using X-ray diffraction proved without a doubt that the electron has a wave nature. And one kind of interesting thing here is that J.P. Thomson here is the son of J.J. Thomson, who discovered the electron originally. Oh, that'll blow your mind, right? So his son figures out that electrons aren't particles, but that they actually can act as a wave. So now, not only do we say that electrons can act as a particle or a wave, but so can light. So you've got this crazy notion, and what we're finding is that we're getting small enough in our size that this idea of energy and matter is kind of blurring between each other, right? So the matter waves aren't really that important to us, but to electrons, they definitely are. So I'll take your questions in class, but that's just a little general background. Now we're going to talk about the wave nature of electrons later, and that's why I kind of brought this up, because the wave nature of electrons is going to have a huge impact when we start talking about uncertainty principle and quantum mechanics itself. But this is where it all started at the turn of the century in the early 1900s. All right, thanks guys. I'll see you in class.